Hello, chemist. So a couple of things that I want to mention. In this video, you are going to be covering periodic trends. And so what periodic trends are is patterns seen throughout the periodic table, whether that be across a period or down a group. There are different categories within this, and so there's quite a bit of information, so you may want to take this slower. Please make sure you're listening, because I promise you this time around I did not type everything that I'm saying. So if you're really not listening right now, that really actually kind of sucks. This is chapter 5, section 3. If you do have any questions, please make sure that you are asking me at the end of the videos. That's really how I help shape the class and the discussion. So if you say you have no questions, I assume you understand. Okay, so the first periodic trend I want to talk about is known as atomic radius. And I just noticed that I did not put an objective slide on here, so my bad. But there are a few things. The biggest thing you're going to learn about is periodic trends for various different types of things on the periodic table. So at this point, you should know some things about the periodic table, including how it's arranged, which is by atomic number. You just took a quiz over there. That elements and vertical groups have similar electron configurations and chemical properties. We are going to go through that in class again. But as we go down a group, they have similar properties, as in like all of the alkali metals are very reactive metals. So those are the kind of properties that I would expect you to know by this point, and that you'll see the similar patterns with their electron configuration. Again, this is something we're going to review in class. So in more detail, we are going to go over atomic radius. And so what atomic radius is defined as 1/2 the distance between the nuclei of identical atoms that are bonded together. And so why we're learning about this is because we are trying to define the size of an atom. And so a good way to determine this would be the distance from the nucleus to the edge of the electron cloud. However, orbitals are super weird because we don't really know where they start and where they end in regards to the electron cloud. So it's a lot easier to measure the distance between atoms that are bonded together. And so that is why whenever you find an identical or two atoms that are identical to one another, you measure the distance from their nuclei and then divide that by 2. And that gives you a rough estimate of what the atomic radius is. And so why this is important is because this is the first periodic trend we are going to look at. How you'll see this is that a periodic trend, before we continue, you should know that a periodic trend is a repeating pattern found across periods on the periodic table. So from left to right is what I'm always going to talk about. And you should know that atomic radius decreases from left to right, meaning as I go from the alkali metals to the noble gases, the atomic radius is going to decrease. As you go down a group, and a group trend is a repeating pattern found going down a group, atomic radius increases going down the group. So from the top to the bottom, as in from period 1 to period 7, the atomic radius will increase. Another full disclosure is that all of these trends are general trends across the periodic table. There will always be exceptions to these rules, so I will point those out, especially when we talk about it in class. But for right now, I do want you to know the trends on how they look. Do not worry about the exceptions to all of the rules just yet. We will get there. So you should have some basic understanding of valence electrons. I'm assuming from Science 1, you have that background knowledge. And so we are going to take that knowledge and we are going to extend it and make it and expand it even further. So at this point, I would expect you to know that the maximum number for an atom in its ground state is 8 electrons in the outer shell, meaning that 8 is the magic number. 8 is what makes an atom stable. So all of the noble gases in their outermost shell, they have 8 electrons. That's what makes them super stable. That is what keeps them from wanting to bond with anything else. They have no reason to. They don't need an electron. They don't want to give anything up, because gaining or losing for them will create an unstable state. Every other atom on the periodic table wants to be like the noble gases and get 8 electrons. So valence electrons will always be in either the S or P sublevels. Remember when I talked about the transition metals, they have very weird rules when it comes to valence electrons. So we're really going to just focus on the S and P groups, or the blocks, S and P blocks. outer electron configuration and the number of valence electrons are the same. And so what I mean by this is if you look at group 1, the outer electron configuration will always be 1s1, 2s1, 3s1. And yes, there is more to that, but it'll always end in that one number. That very last number on your configuration indicates the valence electron number. So if you look at group 2, it always ends in 1s2, 2s2, 3s2, 4s2, so on and so forth. And that 2 indicates the number of valence electrons. I will show you this in class, and I'll show you a nice little table, or I'll have you write down a nice little table to help you with this. But again, the outermost electron configuration helps indicate what the number of valence electrons are. So remember, we did establish that all of group 1 have one valence electron, and you can easily infer that just looking at the group number. But when you get to like groups 13, 14, 15, 16, and 17, sometimes it can be confusing, because if you don't remember the rule of 8, then you're going to probably be like, well, they have 17 valence electrons, which is not a possibility. We are going to extend on valence electrons and forming ions in the next slide. All right, so forming ions. This is possibly one of my favorite parts of chemistry. I love ions. I think bonds are amazing, and making things come together is pretty fun. So hopefully we spend a good amount of time in the lab doing this, or doing some low-level stuff like that. Nothing exploding, hopefully. So many chemical compounds consist of particles called ions. And the reason why many elements or atoms form ions is the fact that they are not stable in their neutral state. So they want to be stable, so they'll either gain or lose an electron. So an ion is an atom or group of bonded atoms that has a positive or negative charge. Two things you should know in theory: there are two ways to gain or lose a charge. One way would be to gain or lose a proton. The other way is to gain or lose an electron. Now, gaining or losing a proton completely alters the identity of an atom. So again, that is a theory. It is not something that anybody in the lab has done, but that is a part of the theory. So in chemical reactions, proton numbers actually do not change. So electrons, on the other hand, though, they are very capable of movement within an atom. They are in that outside, they're not in the nucleus, so they're on the outside electron cloud. So it's very much easy for atoms to trade off or gain or lose them. So what happens is ions are formed, and ions are formed when an atom gains or loses electrons. Again, I'm talking about stuff that I feel like you may know. If you don't know, it's okay. Couple of quick things is when an atom loses an electron, it becomes a cation, and it has a positive charge. I know that sounds kind of weird, but the reason for this is because it has more protons than electrons. So that positive charge is present there. So it becomes a cation. It has a positive charge. It's represented by a plus sign. And that plus sign is like a subscript. I will go into more detail on this in class. On the other hand, we have what's known as anions, and these actually gain electrons. So it becomes more negatively charged because it now has more electrons than protons. And it is represented by a negative sign as a subscript. And you'll see things like 1 plus, 2 plus, 3 plus. That's generally most of the ions there. So we took a quick break from periodic trends, and now we're going to get back into it. Let's look at ionization energy. So quick reminder, periodic trends are trends you see going across the periodic table. Group trends are trends that you see going down the groups. To make an electron jump from a lower energy to a higher energy level, there must always be an input of energy. And so remember, when we're talking about ions, it requires energy in order to get that electron to be gained or lost. There's always energy that is involved. So we have this this term known as ionization energy. And this is the energy required to remove an electron from an atom. So if you're removing an electron from an atom, you are becoming what? If you said anion, you are correct. The periodic trend for this looks something like ionization energy of atoms generally increases from left to right. So as you go from the alkali metals to the noble gases, the ionization energy generally increases. As you go down a group, the ionization energy generally decreases. Now, there are quite a few exceptions to this rule. We are not going to spend a lot of time talking about shielding, and I really just want you to know the periodic trend and the group trend. But one thing I do want you to know is that if an atom loses more than one electron, more energy is required. So let's say an atom has the capability to lose 1 electron, 2 electrons, or 3 electrons. In that case, there are different levels of that ionization energy. So if an atom loses 1 electron, it is just known as ionization energy. If the atom loses 2 electrons, it's known as second ionization energy. And there's more energy that's required from that element. And so I'm going to show you a table, and you'll see that in this table, there is an increase of energy as you progress on. And again, as that pattern continues, so it would be 3rd, 4th, 5th, 6th, so on and so forth. And again, that energy will be greater with more ionization. The next trend we are going to talk about is known as electron affinity. Electron affinity is energy change that occurs when a neutral atom gains an electron. So we just talked about ionization energy, and this is when an atom lost an electron. So now we're going to focus on electron affinity, is where an atom gains an electron. The periodic trend for this is that in general, electron affinities increase from left to right. So that means going from the alkali metals to the noble gases, you'll have an increase. They become more negative. As you go down a group, electron affinity decreases going down a group. They become less negative. And this should hopefully make sense, because your group 1, 2, and 13s elements are not going to be gaining electrons. And I'm going to explain this on the next further slides, but these are commonly your cations. They are going to lose electrons. Your nonmetals typically gain electrons, and so the electron affinity going towards the nonmetals increases. All right, so ionic radius. And so now we're going to focus on looking at what an ion looks like compared to its neutral state. So groups 1, 2, and 13 are metals that lose electrons to form cations. This is a general rule. I honestly have not ever seen an exception to this, like as in they'll never gain electrons. And the reason for that is that the energy required to gain electrons is more than the energy that is required to lose an electron. So you always go with the use of less energy. And so that's what groups 1, 2, and 13 do. They lose electrons to form cations, and they lose these electrons to nonmetals. So a lot of times you're going to see metals and nonmetals bond to create your ionic bonds. Groups 16 and 17 are nonmetals that gain electrons to form ions. So really, it's a beautiful relationship when you have groups 1 and 17 see each other, and they're like, hey, you have 1, I have 7. Let's get together, and we form a full shell of 8, and we are now stable and very happy. So cations are smaller than their neutral element, anions are larger than their neutral element. Right now, that's all I want you to know. And of course, the periodic trend, which is that from left to right, cations decrease in size. So as you go across, your cations are going to decrease in size. Sorry, I didn't mean to move that. All right, electronegativity, and we're almost to the end, so don't worry. I know you're like, what is going on? Electronegativity is the measure of the ability of an atom to attract shared electrons when the atom is part of a compound. So how is this different than electron affinity? Electron affinity is a measure of the actual energy released when an atom gains an electron. Compared to that, electronegativity is a relative scale, so it's not measured in units of energy. All elements are compared to one another, and the most electronegative element, fluorine, is assigned an electronegativity value of 3.98. It is super electronegative, and so it's going to attract electrons better than other elements. So it's going to have more pull, if you will. Since metals have few valence electrons, they tend to increase their stability by losing an electron compared to your nonmetals, which have more valence electrons, and they increase their stability by gaining. The electronegativities of nonmetals are generally higher than those of metals. So the trend goes across the periodic table. Electronegativity generally increases from left to right. As you go from metals to nonmetals, your electronegativity is going to increase. And the last but not least slide is on metallic and non-metallic characteristics. So pure elements with a high metallic character are generally very reactive. And I'm looking at like the alkali metals, the alkali earth metals. These are very reactive elements. They are hardly, if ever, found in nature by themselves. they are so reactive that it's incredibly dangerous to deal with these in their neutral state. So a lot of times you'll find these bonded. For example, sodium, super reactive. Chlorine, super deadly. Come together, they become salt, which is super tasty. So, I mean, really, it's a beautiful relationship with these valence electrons. And like I've already said, metals tend to lose electrons due to low ionization energy. They don't have that pool in comparison to nonmetals, that they have these nice pool, this big ionization energy, so they can pull these electrons from these metals and say, hey, come over here. It's almost like they're lassoing the metals, and they're saying, you are going to come with me. It's a very one-sided relationship, if you will. All right. That is all I have for you today. In class, we are going to make we are going to label our periodic tables with periodic trends. If you have any questions, please make sure to ask me on Edpuzzle. See ya.